Okay, so welcome to Math 389 Advanced Analysis. So this is lecture 10. And so we're going to talk a little bit about mean of means, but not too much because I've heard several of you are working on this and are going to present more on this on Thursday. So I'll just say a little bit. We'll talk about derivatives of infinite sums. And then, as always, when you guys tell me what you're interested in working on, I can work that into the class. I know at least one of you is working on something where a certain integral and an interchange is important. So we will talk about that interchange and is this justified or not. Given that it's related to his thesis, it would probably be very nice for him if it could be justified. So, we're supposed to be impartial, but it would help. All right, so I wrote, some, simple programs. Tm was the triple mean we were looking at. Xy plus yz plus xz over 3 to the 1/2. And then, I looked at, 9Tm was just the triple mean of the triple means. This is somewhat bad notation because this is not the only possible triple mean we could do with three variables x, y, and z. If we had the arithmetic mean, we had the geometric mean. Is there anything else we could have had here? Or is this the only other thing? This is the only other linear thing. So actually, it's not terrible notation here. Once we get to 9, there's lots of different possibilities. So this was bad coding, where I said, well, look, I'm just doing a really quick test, so I will have 9 random variables, A, B, C, D, et cetera, et cetera, et cetera. Just plug them in and just check and see, does it work? And so I had it printed out, and I did it for 1, 1, 1, 1, 1, 1, 1, 1, 1, Y, and then I did, K, because what I was doing is I was comparing this to the 9 different means. And the 9 different means come from taking, the product. And so here I actually wrote the code a little bit nice, X is going to just be my numbers 1 through 9. I'm going to take a subset of them of a given length. The length will be K, and I'll just take X for those indices. And I'll just take the product, take the sum, divide by the binomial coefficient, take the appropriate root, and this will calculate all those. And if the triple mean of the triple means is going to be one of these means, then it has to be true for all values of inputs. So let's do all ones in a Y. And if I do all ones in a Y, we see that it looks like a Y to the 1/4. So the only thing that could possibly work would be K equals 4. And a little bit of work shows that it's not going to be correct. You can put in specific values of the numbers. I might have done that later, maybe not. Okay. This is a slightly better version of the code. Rather than putting in 9 variables, just put in a list called numbers. And then I'll just let X be numbers so I can just do things to it. And so that's a little bit faster, but it's the same code. And not surprisingly, same results. I then tried to look at all different ways of doing things. If I have 3 numbers and I want to do a mean of 3 numbers, well, I have 3 different means I could do. And so I tried looking at all these different combinations to see if any of them worked. And I would have been more excited right now if any of them worked. And so just printing out all the different pairs, nope, nope, nope. Nothing is working, nothing is working. They start to get more and more involved. Nothing works. Then they start getting better as you have more and more things in terms of the products, the number of terms in the products, you have fewer sums. So it gets a little bit nicer. Nothing worked. This leads to, I think, the natural question, which some of you are looking at, is how many means can we create satisfying the properties we care about? So if we start grouping things, so if we give up on the symmetry, if we give up that if I permute the numbers, I should get the same result. Well, I mean, to some extent, we should now have infinitely many, because if you've ever taken a class, not every professor chooses the same value for the midterm versus the final versus, you go to the British system, and it's essentially like a delta spike at the final exam at the end of possibly the year, right? And so once we do something like that, we have infinitely many possibilities. So if you want to have finitely many possibilities, you want to put in some kind of constraints as to what do you consider. It's like playing with Lego. I'm sorry, not playing with Lego. Teaching with Lego. I teach with Lego here. If I give you 2 Lego and I ask you how many ways can I combine them, if I'm allowed to pivot at an arbitrary angle, there's infinitely many possibilities. And you could look at maybe a dimensional space. If you now restrict yourself to they have to be at right angles or parallel, now all of a sudden the problem becomes incredibly difficult combinatorics, but finite. And so hopefully on Thursday, we'll hear a little bit more about some of this stuff. But
and also I think numerical value of the triple mean is the closest to actually the fifth
yeah,
mean.
which you said was interesting that it's closest to the fifth, which to me doesn't make sense as y gets, if you keep everything at 1 and let y get very large, then the triple mean of the triple means is going to look like y to the 1/4 with a constant.
Yeah.
Whereas you're going to get different constants, but you're going to get a different power of y. And so part of it could be close in what metric and close in what regime.
Yeah.
And for certain values, one thing might be a better fit, but as y gets enormous. And then of course the other thing is this is the ridiculous extreme where 8 of the inputs are 1 and 1 input is very large. Sure, in that case, maybe the k equals 4 does better than k equals 5. But maybe for some generic case, let's assume we take all the inputs to be uniform from 0 to 1, some nice box. Or maybe we choose a point inside a sphere of radius 1 in 9-dimensional space that gives me that coordinates. Maybe in something like that, maybe the k equals 5 does a better job. So I wouldn't be surprised if something else does a better job. The question is, 4 and 5, there seems to be a nice reason for something like that. That is kind of the middle from 1 to 9. So is something like that going on? If there's interest later in the semester, maybe I'll show something interesting related to E and the numbers 2 and 3. All right, so the first thing I want to do, well, want is the wrong word, but I think have to do, is I think we have to justify differentiating an infinite sum. Because you've basically told me you haven't seen this, and you are math majors, you represent Williams. I've heard rumors that you don't have to do mechanics in some schools to be a physics major. I don't want to know if that's true. Okay, so do not do any body language to let me know if that is true or not as to where. But differentiating an infinite sum. Term by term. Now we did this special case of a geometric series. So my first question to you is, do you remember all of your tests about when a series converges? Do you remember the ratio test, the root test, and stuff like that? So we'll say, some, an x to the n converges for x less than, let's say, r, if the limit as n goes to trivial, we'll fix this in a moment, of the absolute value of an to the 1 over n, if this is less than 1 over r. I'll say converges absolutely. And I guess it's not say, I guess this is like a theorem. So this is the root test. If the nth root of the absolute value of an, and technically I can't write lim, what do I have to write? I have to technically write lim sup. If the lim sup of the ans. And let me just sketch the proof. So assume the lim sup of an to the 1 over n is less than 1 over r. So there exists an epsilon greater than 0 such that for all n greater than or equal to some n, we have the absolute value of an to the 1 over n is less than 1 over r plus epsilon. Because if the lim sup is less than 1 over capital R, I can write that number as some number. If epsilon equals 0, then it's 1 over r. So I just keep increasing epsilon until I get to that number. And so that will be strictly less than 1 over r. Thus, the absolute value of an to the 1 over, absolute value of an would be less than 1 over r plus epsilon to the n. So the absolute value of an x to the n would be less than r over r plus epsilon to the n if the absolute value of x is less than r. So converges by a comparison test. And what series are we comparing it to? With geometric, which geometric? You have to say what the ratio is. R over r plus epsilon, which is less than 1. So really what the ratio test and the root test are doing is they're just doing a comparison test. The comparison test is really easy to do if you know what to compare it to. Yeah, this is the divine inspiration. I happen to have the insight to compare it to this sequence. It's absolute values less than this sequence term by term, and that sequence converges, therefore it converges. Great. How did you think of doing that comparison? What the ratio test and the root test are doing is they're just doing that under the hood. They're hiding how they find what to compare it to. But it's really just a comparison with the geometric series. So we're comfortable that if you are inside the radius of convergence, you converge absolutely. And again, it's dominated by convergent geometric series. We don't really have to worry about rearranging terms because the tail is small. Thus, the tail is small. Okay, that's the huge advantage. Okay, so now what we want to do is we want to differentiate term by term. Okay, so let's let f of x be the sum, n goes from 0 to infinity of an x to the n. We can write that as the sum, n goes from 0 to capital N of an x to the n, plus the sum, n goes from n plus 1 to infinity of an x to the n. Call it the sum, n goes from 0 to infinity an x to the n plus, let's say, gn of x. Does gn of x converge? What do you think? Shouldn't it converge? It's just the tail. We start off with fx as a convergent series. This is the series from before. Yes, so long as x is less than r, the radius of convergence. So as long as we stay within the radius of convergence, the series gn of x converges. Oh, and that should probably be a capital N, not a lowercase n. What can you tell me about the size of gn of x?
Wait, did you mean at the very end?
Oh, sorry, no, not 0. Sorry, it's not 0. Sorry, from n plus 1. Oh, no, that was fine.
0 to n, right? 0 to capital.
Oh, 0 to, sorry, this should be 0 to n. Yes, sorry. Thank you. I'm just calling the second part gn of x. Yeah, sorry. So we're just taking the tail, calling it capital, g capital N of x. Is g capital N of x large or small as n gets large?
Oh, it grows as n gets larger. No, sorry, it actually gets smaller.
Can't say it gets smaller because it's possible that there's some oscillation in sign. So maybe I have some. So maybe I have some cancellation, and that's okay. This is why I don't mind spending a class or two on this because there are so many things that are just instinctive to say that are wrong, but they're fundamentally correct. So it's possible that it gets a little bit larger than a little bit smaller, but we know in the limit what has to happen to gn of x. It has to shrink, it has to go to 0 in absolute value. But it doesn't have to go there monotonically, because if you have opposite signed things, so we know the limit as capital N goes to infinity of the absolute value of Gn of x goes to 0 for the absolute value of x less than r. What about the derivative of Gn of x? Initially, we don't know. And so, again, I don't know if I can quickly find where we had the bad function. Is it here? Yeah, here it goes. We had the function, this is what's so nice about having all the slides. Here we had the function, 1 over 2n sine of 4n x. The different terms are getting very small, but the derivatives were getting large. Why is this not a contradiction to what we're doing? I can't differentiate this term by term, and this converges for all x. Okay, it doesn't want to let me copy it, so be it. I can write it again, I'm a big boy. So can we differentiate term by term? We couldn't for the sum, n goes from 0 to infinity, 1 over 2 to the n sine 4 to the n x. What's different about that and the sum of a n x to the n? I mean, we all agree we're trying to prove that we can differentiate term by term within the radius of convergence. This sum converges for all values of x. Why can't I differentiate term by term? I showed you we can't. I'm now going to prove to you we can. Well, whenever somebody's giving you a proof, before you spend the time trying to understand the proof, check. Let me check it with this. Wait, but that converges for all x. Converges absolutely. Why is there no contradiction? I got 1 over 2 to the n. I got convergence up the wazoo. Say the first series out loud. So the first series is the sum of an x to the n. What's the second series? It's the sum of 1 over 2 to the n times the function sine of 4n x. They're not of the same form. I've written the second one as a sum of functions. The first one I've written as a sum of powers of a very specific function. That's the difference. No contradiction as not a power series. So be very careful to make sure you only use the thing where you can. When we're talking about taking the derivative term by term of a power series, that's fine, but this is not a power series. You want to make it a power series? Go for it. Expand out the sign. Well, what happens when you expand out the sign? The sign of u is approximately u when x is small. So it's going to look like 4 to the nx, right? But it's even worse because no matter what x is, if x is even a small little teeny number, as long as it's not 0, eventually 4 to the n is going to overwhelm x. And so it's going to be all over the map in terms of what this is. So to try to find a Taylor series expansion for this function is going to be hard. Why should you be skeptical about a Taylor series expansion existing for this function? Yeah, but there's okay.
Find the Taylor series need to differentiate.
You need to differentiate, right? If you want to find a Taylor series, you need to take a derivative. We showed this function is not differentiable. I'm not expecting to find a Taylor series. I'm not expecting that this has a power series expansion. Therefore, this theorem should not be applicable. So, again, always be careful. Am I using a theorem in a place where I should be able to use it? And again, I love teaching classes like this where we are not pressed for time and we have to make sure we cover all this stuff because another class is waiting for it. There is rumors of the class that was taught here years ago where they didn't do eigenvalues in linear algebra. Yes, they never let the professor live it down. Okay. I'm not going to go into anything else while this is being recorded, but yes, there was a linear algebra class taught where eigenvalues were not covered. That was bad. Okay. And so certain classes, you have to cover certain material. It doesn't matter what we cover here. We can take the time and really drive home thinking about things. This is what's going to make the difference in your professional career, how to think about things, how to attack things. All right, so let's try to do things term by term. Do we agree that Gn of x is going to be small? But it's possible that maybe Gn prime is going to be large. So the question is, can we bound Gn prime? So how big could Gn prime of x be? And remember, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. That's going to be, for us, the sum, and it goes from 0 to infinity, an times n x to the n minus 1, plus the limit as h goes to 0 of, an x to the x plus h to the n minus x to the n over h. Now just rewrite the an so it's clear that it's multiplying the whole thing. I'm saying here that the limit of the difference is the difference of the limits. So if you don't like that, or I could say it's the limit as h goes to 0 of gn of x plus h minus gn of x over h. And what do we want to show that that limit equals? Oh, sorry, I keep doing this. It's not summing to infinity, it's summing to capital N. Sorry, summing to capital N. What do we want to show that this limit equals? So as big N goes to infinity, what do we want that limit to go to? We want that to go to 0. So if that limit goes to 0 as n goes to infinity, then as n goes to infinity, we just take more and more terms on the left. Does this sum converge as we take more and more terms? So converge as n goes to infinity? Yes. If we take n times an, an absolute value, to the 1 over n, that has the same limit as an to the 1 over n. As n to the 1 over n goes to 1. Does everybody know how to prove n to the 1 over n goes to 1? Take log, right? When in doubt, if it's Professor Miller class, take a logarithm, right? So we'll just do this as an aside. If we look at the log of n to the 1 over n, that's log of n over n. And so the limit as n goes to infinity of the log of n over n, what does that equal? What do we use? L'Hopital. And so you can use L'Hopital and you get that's the limit as n goes to infinity of 1 over n over 1, which is 0. Therefore, that implies the above equals 1. Another way is you could let n equal e to the m, and then the log of n over n is just m over e to the m, which is less than m over m squared over 2, which goes to 0. So if you don't want to use L'Hopital, I can actually bypass L'Hopital by just saying, look, right n is e to the m. I only keep the quadratic term down below. That's enough to show that this is going to 0. So having the n times an, not a big deal. It doesn't change the radius of convergence. So if you differentiate, the radius of convergence doesn't change. All we have to do is we have to show that the limit of gn x plus h minus gn of x over h goes to 0. How can we do that? So we need to study the limit as h goes to 0 of gn of x plus h minus gn of x over h as n goes to infinity.
So use of the interchange.
So if we interchange the limits, then what would the limit of gn be? There would just be no terms. So if I fix h, if I show that if I take n sufficiently large, it goes to 0, and then I can do this for any h, will that be sufficient? Which way do I have to do things? So I want to look at the limit as h goes to 0 of the sum n goes from n plus 1 to infinity of an x plus h to the n minus the sum n goes from n plus 1 to infinity of an x to the n over h. Is this the same as the limit as h goes to 0, the sum n goes from n plus 1 to infinity of an x plus h to the n minus x to the n over h? Can I do that? If I have two series that converge, can I add them inside the radius of convergence? Yes. Right? I can add two series that is the radius of convergence of a sum, the same as if the two series have the same radius of convergence, is the radius of convergence of the sum the same? No. What do you know about it?
If you take one series that's the negative of the others.
Good. If one series is the negative of the other, the radius of convergence got larger. But if I take two series that converge absolutely inside the radius of convergence and I add them, it's got to converge absolutely, at least in that radius of convergence. Maybe more. Maybe I now have some things canceling and helping me, but I know it can't get worse. So I can do this. What can you say about x plus h to the n minus x to the n? So x plus h to the n minus x to the n over h.
So something like x plus h minus x times something that involves x plus h plus x. And then the h can cancel with the h. And then because h is small, all the
Right.
terms are going to be roughly the same. Something else to the pseudo-power.
But I mean, we would love to just move the limit on h inside. What can you say about the difference between x plus h and x?
It's h. You just factor.
You can factor this. So this is the same as x plus h minus x to the n. So we're looking at a to the n minus b to the n is a minus b times, I think it's a to the n minus 1 plus a to the n minus 2b plus dot 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 plus a b to the n minus 1 plus, sorry, b to the n minus 2 times b to the n minus 1. That's the factorization, right? The difference of two nth powers. A squared minus b squared is a minus b times a plus b. A minus b cubed is a minus b, a squared plus ab plus b squared. So now, this is just x plus h minus x, that's the a minus b. And now we have x plus h to the n minus 2 plus x plus h, sorry, to the n minus 1. Then x plus h to the n minus 2 times x plus dot 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 plus x plus h x to the n minus 2 plus x to the n minus 1. Yes. Okay. So this is equal to, and we divide by h, right? So we factor out the x plus h minus x over h. That's just 1. Did I make a mistake? No, that's fine. Okay. So that's going to just be 1. And now we have x plus h to the n minus 1 plus x plus h to the n minus 1 times x plus dot 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 plus x plus h x to the n minus 2 plus x to the n minus 1. Okay. How big can this be? How many terms do we have? N terms. So this is going to be less than or equal to n times the maximum of the absolute value of x, absolute value of x plus h, raised to the n minus first power. Right? So if the absolute value of x is less than r, choose h so that x plus h in absolute value is less than, let's say, r minus epsilon tilde, which is strictly less than r. So because we're within the radius of convergence, as long as I don't move too far away from x, I'm still in the radius of convergence. And so we now get the limit as h goes to 0 of gn of x plus h minus gn of x over h is going to be the limit as h goes to 0 of the sum n goes from n plus 1 to infinity. We'll have our an, I'll put in absolute values, and then we're going to have n times, let's say, r minus epsilon tilde to the n. Is that going to converge? The extra factor of n, is that going to change the radius of convergence? No. And so this is going to converge, and because it's the tail, it's going to go to 0. So it converges and goes to 0. So one of the challenges of teaching an upper level class is always how much detail to go into. At what point can I say this is enough detail so that you see the broad brushstrokes of what do you need to do to prove this rigorously? And the main idea is, we're using the difference of n powers. And so if we have a to the n minus b to the n, we know a minus b is a factor, so it's around h. We get this extra factor of little n, which could be annoying, but it's not going to change the radius of convergence. So since it's not going to change the radius of convergence, I'm not that worried about it. We can bound things without too much trouble, and we can now justify differentiating term by term. So for those of you who took complex analysis with me, this is something that I implicitly assumed you had seen in real analysis. It's something that you need to be able to do. Okay, any questions about this? And since this is being recorded, and I don't want to have a recording error, I will just leave it at that for now. All right, so how many of you have seen the error function? Yeah, I'm not thrilled with the name. The name, I think, has some negative connotations. But one of the things that's also annoying is, who are my physicists again? Please raise your hand. Okay. Three-dimensional space, spherical coordinates, what is the angle coming down from the z-axis? So you said theta, phi. If you're a physicist, it's theta. If you're a mathematician, it's phi, and they keep theta for the plane because that's reduces. I learned, unfortunately, spherical coordinates in my physics class as a freshman before we got to it in my math class. And so I have to resist every time I teach 150 here from using the physics notation of having theta as the angle coming down. It just, I have to fight it. I actually like having the theta coming down because it's typically that's the angle that has the interesting asymmetry in the problem. You just have to be careful as to which language you're speaking, what notation you are using. And different sources, different books will define things differently. There are at least 3 different definitions of the Fourier transform. It involves where you put the 2 pi. Sometimes it involves where you put a minus sign. And then there are some people who like to basically appease everybody and take a square root of 2 pi to try to split the difference. You've got to just check and make sure that you have things normalized properly. In my first sum of doing small, one of my students had a phenomenal result, except for the fact that the Fourier transform was not normalized the way he thought. And when you put in the correct normalization, his result collapsed. And it was now trivial support rather than something phenomenal. So you've just got to be careful how you define things. So the standard normal hopefully everybody has seen, the density is f of x is e to the negative x squared over 2. And then you would have a 1 over square root of 2 pi, so it integrates to 1. More generally, it's 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. That's the more general normal distribution. We normally do mean equals 1. Mean equals 0, variance equals 1. For the error function, I always forget how they define it. I think they don't have the 2 in the denominator. I'm not sure. So one of the big things you want to be able to do is find the area under curves, because in probability, area under curves, that's what we live for. It's the probability something happens. Unfortunately, if you have taken calculus 2, you learned a bunch of integration techniques. And you got a very false impression about your abilities. You can't integrate. You can do a few very carefully selected functions and get something in closed form. But if I write down almost anything, you can't get a closed form antiderivative. If I give you, I don't know, integral of cosine of x, is there a nice antiderivative for the integral of cosine of x? What is it?
So
Okay. And what is the sine of x? How do I compute it?
you get its expansion.
Well, I'm saying, okay, so I want to calculate the sine of 1.37. There's been an electromagnetic pulse. It's really sad. All the electronics have, somehow my jumbo iPad is still connected over here. Everything else, it's the advantage of being in the basement. Calculators have failed. Web is down. How do you calculate the sine of x?
Approximately X.
I don't care about approximately. How do I calculate the sine of x? There's no lawyer here who's going to sue you if you
Scalar expansion.
say, okay, there we go. So the sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus da, da, da. So in some sense, you say, well, the integral of cosine, it's trivial. It's sine of x. Well, what is sine of x? It's this infinite Taylor series expansion that we've given a name to. So when you say that cosine has a nice antiderivative, you're really just saying you've given a name to its antiderivative. And so in mathematics, they do have the error function. And I guess for completeness, I will gamble that the web is working just for a moment and just go online and look up and see what is the error function of how do they define it. Because, again, for a lot of these things, it depends on where you want to put your twos. And so I wrote Wikipedia, fountain of all knowledge, source of all wisdom. And Wikipedia doesn't want to load. So I guess we are. Okay, here we go. So yeah, I was correct. It defines the error function without the 2. So the error function of z is defined as 2 over the square root of pi, integral from 0 to z of e to the negative t squared over 2 dt. So this is a normal with, what would the variance be? Oh, sorry. It's t squared. What would the variance be? I don't think 1.
Wait, oh, why is
This is how the error function is defined. It's defined as 2 over square root of pi integral from 0 to z e to the minus t squared.
so like square root? Is it 1/2?
It's 1/2. I said variance, not standard deviation.
Oh.
Right. So you can define it however you want. This is a convenient definition because now you don't have that factor of 2, and if you expand things and whatnot. So in probability, x is a random variable. How many of you have taken probability? Okay, almost everybody. Do you understand? Have you seen the basics? PDF, CDFs? Okay. A random variable with PDF, F, and CDF, capital F, means the probability that capital X is less than or equal to, say, little x, is big F of x, is the integral from minus infinity to x of f of t dt. If you have more than one variable under discussion, you often put subscripts on the f's to indicate which variable. When there's only one variable under discussion, there's really no need to overload the notation. You should be thinking fundamental theorem of calculus when you see this, right? The derivative of the CDF is the PDF. Okay. So let's take the standard normal. Okay, so let's calculate the cumulative distribution function. And this should be lowercase x. We use lowercase values for the lowercase for the value it takes on, capital for the random variable. So the CDF at x is the integral from minus infinity to x of 1 over square root of 2 pi e to the negative x squared over 2. I'm sorry, e to the negative t squared over 2 dt. You can see now why they may not want to use the standard normal. Because if you want to, well, what's your first thought when you see this integral? What do you want to do to the exponential?
Substitute.
Yeah, substitute with its. So what should we substitute for the exponential? If I give you the exponential, what should I substitute for it? Well, no. I mean, you have the exponential, you have e to the negative t squared over 2. How do I get a handle on what e to the negative t squared over 2 is? What do I use? Taylor series. And this converges for all inputs, so it's fine. Do you want to keep doing things with the t squared over 2, or do you want to adjust things to the standard deviation equals 1/2? I'm sorry, the variance equals 1/2. Do you want to get rid of the 2 down below?
Yeah.
All right. So let's look at capital F y of x. And that would be the integral from minus infinity to x. And so now we're going to take sigma squared equals 1/2. So 1 over square root of 2 pi sigma squared becomes 1 over square root of pi. So you get 1 over square root of pi e to the negative t squared dt. And so this is the CDF. Okay. And so this is the same as I can pull out the square root of pi. It's the integral y goes from minus infinity. I'm sorry, t goes from minus infinity to x. And then this is the sum and goes from 0 to infinity of e to the negative, I'm sorry, of negative t squared to the n over n factorial dt. So we're using, e to the u is the sum of u to the n over n factorial, and it goes from 0 to infinity for all u. So the sum converges for all u. What should we do? So you get the integral of a sum. I'm sorry. So we have an integral of a sum. What should we do? Interchange, right? The only thing we know how to do, we only know how to do 2 things from Calc 3. Change variables, interchange orders. So this is the same, and I'll put it in quotes because this is a math class, we need to justify it, as 1 over square root of pi, the sum, and goes from 0 to infinity. We'll have negative 1 to the n over n factorial, integral t goes from minus infinity to x of t to the 2n dt. Is that integral easy to do? Can you integrate t to the 2n? Yeah, that's just going to be t to the 2n plus 1 over 2n plus 1 evaluated at x and negative infinity. And now what happens? So what do you get when you do the evaluation? When you plug in x, what do you get? You get x to the 2n plus 1 over 2n plus 1. That's fine. What happens when you plug in negative infinity? Yeah. It's bad, right? It blows up, right? This is not good. How can we get around this? One possibility is instead of going from minus infinity, we could go from maybe minus capital N. So replace minus infinity with minus n, send n to infinity. Now you're okay, but really bad convergence. we have the decay from the -1 to the n over n factorial. It's going to be an alternating sum, but you're going to have an alternating sum of huge numbers that are going to get really large before the n factorial comes into play. You give me any specific value and we'll find out. The Gaussian, we all agree the Gaussian decays very rapidly. So if n is huge, the probability that you're between -infinity and -n is really small. So if I just integrate from -20 quadrillion, sure, that's going to effectively be all the probability. But boy, if I try to numerically evaluate this, it's a nightmare. These numbers are going to be huge. Small little errors in machine precision could be really bad. So in principle, we can make this work with limits, but this is going to be a nasty, nasty limit to do. Now, remember, sine and cosine, you consider these to be nice functions. You've been trained to consider sine and cosine a nice function. It has a name. So we're giving the integral of the Gaussian a name, the error function. I think the name is a little bit misleading. I think it's nicer than it sounds. But if we give something a name, it shouldn't be too bad to work with. This is not pleasant to work with. Is there any value of x where you know the probability of getting a value from the Gaussian of x or smaller? Okay, and what's that at infinity? 1. Is there any other value you know? 0. What's the value at 0? 1/2. So this is the trick. And so what we do is here is 0. Here is our distribution. And we know that the probability up to here is 1/2. So what we do is we define the integral from 0 to x. So the error function of, and I think they were using z, so I'll replace x with z. I'll switch to the eraser. So the error function of z, I think, was defined as 2 over square root of pi. Integral from 0 to z of e to the -t squared dt. Really, what that's doing is this is finding the area. Here's 0. Here's z. Here's -z. And it's finding the area between -z and z. So this is just the probability -z less than equal to y less than equal to z. And so now, if we try to play the game as before, the error function of z is 2 over square root of pi, integral of 0 to z, the sum, and it goes from 0 to infinity, e to the -t squared dt. Now, if I interchange the sum and the integral, I actually have to put in the Taylor series expansion. I just can't put the same function back again. E to the -t squared to the n over n factorial. I'll get -1 to the n over n factorial, integral 0 to z, t to the 2n dt. And now that's 2 over square roots of pi, the sum, and goes from 0 to infinity, -1 to the n over n factorial. And now I'll get z to the 2n plus 1 over 2n plus 1. And that converges nicely. And so can I now use this to find the probability that y is at most z? So what is the probability that y is less than equal to z in terms of the error function of z? Let's assume z is greater than equal to 0. Just make your life easy.
1/2 plus half error.
Good. It's just 1/2 plus 1/2 the error function of z, or 1 plus the error function of z over 2. If z was less than 0, could you handle it? So you just subtract. So you would, again, take half of it and then subtract that from a half. And you've got to be a little bit careful. In my expansion here, am I assuming z is positive or negative? Or am I not saying? I mean, nothing in my expansion in gold depended on z being positive or negative. It's just, if I want to interpret things, can I interpret this as the probability that you're between minus z and z? If z is negative, do I have that interpretation?
Still,
I'm sorry?
you still have this, because now the error function is going to be negative.
Right, so I'm saying if I replace z with negative z, if you look at it, the integrand is an even function. So I replace z with negative z, I've basically just taken the negative of what I have. So it's not going to be the probability. It's going to be very nicely related to the probability.
Yeah.
So in fact, if I just use this expansion with negative z, then that gives me exactly what you want, 1/2 minus the error function. So this is actually true even if z is negative. So it holds if z is less than 0 as well. So this is a nice example of interchanging order of operations, which is the technical part of the class. It's related to a problem I know somebody in the class was looking at right now. If we want to use expansions, we have to be very careful to use the right expansion at the right time in the right place. When we started today, we had a series expansion in terms of x. And then we had another expansion in terms of sines. There's a huge theory about expanding things in terms of sines and cosines. It's different bases. Linear algebra, to a huge extent, is all about finding the right base for the problem. In linear algebra, you might have seen the principal axis theorem. You've seen eigenvalues? Okay. Have you seen how to write conic sections with matrices? Okay, so in high school, you learn about writing an ellipse, for example, if it's aligned with the coordinate axes. And here's A, here's B. You get x over a squared plus y over b squared equals 1. Beyond high school, however, people become nasty and say, well, what if I give you an ellipse that's not aligned with the coordinate axis? Then what you say is, well, it's really not a big deal. All I have to do is just go at an angle. And in this UV space, it's u over a squared plus v over b squared equals 1. And then how do I get from xy to uv? A rotation. So again, I may get things slightly wrong in terms of physicists and mathematicians have the minus sign in their rotation matrix in different places. So I will just say there's a rotation matrix depending on theta that takes x and y to u and v, and not worry about which way I'm doing. So are you rotating the axes? Or are you rotating the vectors? Right. And now what you can do is you can see that you can write your ellipse as like xy rotation matrix theta inverse, which is just negative theta. 1 over a squared, 0, 0, 1 over b squared, rotation matrix xy. Okay. And so this is a great way of saying, look, if I want to study the ellipse, change to the coordinate system where the ellipse is nice, study it there, and then change back when you're done. And so we first rotate to the UV space, and then we rotate out of the UV space back to the XY space. It's all about finding what is the right coordinate system to study things. When you're doing calculus, the very natural coordinate system to study is 1x, x squared, x cubed. This gives you Taylor series. You don't have to use that. You can use, sine nx, cosine nx, or e to the I nx, and you get Fourier series. And depending on the problem, different bases are better. So if you've done physics, you might have seen some situations involving like heat problems, wave motions, where the Fourier basis is more natural to study things. There's other bases. And this is where you get wavelets. Again, it's just worth knowing a little bit what's out there. And your different bases have different nice properties. A lot of it comes down to how do they interact with different differential operators? Are they nice solutions? Are they eigenfunctions of different differential operators? And that's what's really lurking in the background. And so whenever we're doing these calculations, it's always, where should we be living? We're used to expanding things in terms of 1x, x squared, but those basis elements aren't necessarily the greatest. If we're looking at the intervals 0, 1, okay, then it's not so bad. They're not getting too large. And then you might want, what might you want to be true about your basis directions? Right-handed. So how do you generalize? And this is where you have the integral dot product. You want the integral of f of x g of x or f of x g bar of x. That's going to be your dot product. And so here, what I was trying to do is mix two different things and talk about, instead of expanding things in terms of a power series in terms of x's, I was expanding it in terms of functions. And it's fascinating because each individual function is being multiplied by such a small number that the contribution to the value is insignificant, but the change becomes huge. And we can't even write down a Taylor series expansion of this. So here's a nice continuous function that does not have a Taylor series expansion. So this function's, it's not differentiable. It's easy to prove it's not differentiable at 0. It's not differentiable anywhere. So we then went from that to looking at, trying to find the area under the standard normal. And at the end of the day, we finally got this nice result that the cumulative distribution function is 1 plus the error function of z over 2. And so now if we want to find the derivative, well, that's not a problem. We have a formula for the CDF. The CDF involves the error function. We actually have a Taylor series expansion for the error function. Is this a good function? Do you consider the error function a good function? It seems decent. I mean, when you compare it to the exponential function, how different is it? Okay, yeah, you get the -1. Interesting. Normally it ends around 17%, but I did start with 4% less battery than normal. You've got the extra 2n plus 1 that even gives you more decay. It's got better convergence property. It's got alternating sign. You could make the argument that this is actually better than the exponential function. But what nice property does the exponential function have? Yeah, it's derivative itself. I mean, that's a tough thing to beat. This is not going to equal its own derivative. But it's not a horrible function. We can give it a name. And so I just want you to be aware that just because something has a name doesn't mean it's good. Just because something doesn't have a name doesn't mean it's bad. A lot of it comes down to what is used. We use sine and cosine so often, we don't think twice about it. But if you had to calculate sine and cosine, what are the only sines and cosines you can compute? 0. Where do those come from? What are the only angles we can compute?
triangles.
Right, good. So what are the nice triangles?
30, 60, 90, 35.
So it's the equilateral triangle, and cutting that in half gives you the 30, 60, 90, because these are all one. And what's the other nice triangle?
45.
Yeah, that's it. These are the only nice triangles. Anything else is now we use the trig rule. So we have angle formulas for the angle addition, for half angles and whatnot. So you give me any number, and I can write it in terms of, go 45 degrees. If that's too much, just go 22.5 if that's too much. And then just do like a binary decomposition in terms of stuff like that. So we can come up with these formulas to calculate. So once we know the sign of pi fourths, we can get everything in terms of these nice infinite sums. And the only times things simplify nicely is coming from these two triangles. All right. So I think this is a good place to stop. Again, I hope you got a sense of the challenges of interchanging operations, that sometimes you have to be clever. And the only reason this worked is because we know that the probability is 1/2 up to here. And that was the source of everything working. All right, to stop.